Okay, so the first lecture is what is an image. So an image is color images, we have gray images, and actually an image is just a matrix of numbers. So it is, if you make a zoom, so at some point what you have are samples. So, and in these samples, what you have are values. And these values, typically, they can take any range, so they can be from -1 to 1, from 0 to 1, but a very typical range is from 0 to 255. That are the gray levels that you can have with 8 bits. But in general, it can be anything. It is just a number. And this number, the larger it is, the brighter that point is. So 255 is white, 0 is black, or green. This actually you see here. So this 75 is the smaller numbers. So it is the darker pixel. And the same for color images. Color images, you have 3 numbers, one for the red channel, for the green channel, and for the blue channel. And in each one of the channels, you have a number from 0 to 255. And again, the larger the number, the more intense is that color. So an image is just a matrix. It's a matrix of numbers. You can think of it also in this way. So you can think of it as, let's say, I want this folder. And so let's say that you have an image. So you have some image there. So you have 2 axes, X, Y. And actually, the typical way to have axes in image processing is not this one. It doesn't matter which one you choose, but the typical one is this one. Y and X. So this point is 0, 0. So this is a continuous image. So it is something that is defined for every location. So this image is defined for every location. For every location, you will have a value. And then this will be a continuous image. This would be a continuous image. And you could have a digital image. A digital image is the one that we have shown in the slides. So the digital image is somehow, and we will talk about this. So it is somehow quantized in the space, and it is also quantized in gray levels. And we represent them as X and Y. So I'm using the same notation that you were using in signal processing, where square brackets were for discrete signals and parentheses were for continuous signals. So these are discrete values like 0, 0, 1, 2, 3, 1, 2, 3. Here you can have the image at any possible location, 0.5 if you want. So this one would be a discrete image. So the relationship between the two is the same one as the one that you have between 2 continuous. So you have time, you have X of t, and then you have some signal here, and this would be the continuous signal. And you would also have the discrete signals, X of n, and then you would have samples of the signal, whatever, zeros or whatever. So it is the same concept between continuous signals and discrete signals. And actually, the how did you, what is a signal? So a signal is something that takes an argument and returns another value. So this is called the domain. I will make the domain green. Green. Yeah. So this is the domain. The domain is this T, and I said green. Domain. I will get the right domain. This is the domain. This is the range. Range is red. So range is red. So when you say continuous, you're referring to the range. So something is continuous because the range is continuous. Okay, and if you want all this is the range. So this is the result. What about a discrete image? So a discrete image, x of n, goes from an integer to some real value. So when you say discrete, okay, I did it wrong. So discrete or continuous, they were referring to the domain. Okay, so let's make it like this. So this is nice that we have, let's see, yeah, this one. So excellent. So in this coloring notation, the domain is the one that is discrete or continuous, and the other one, range. In this example, so it is always continuous. Okay. So when you say discrete or continuous image, you are referring to what is the domain of that function. And the same applies to images. So when you have an image, these continuous images, in general, I will call them R with a vector. And so R with a vector goes from R squared to here, let's say it is a gray image. So it is real. And here in the discrete images, so in the discrete images, so the discrete images, now it is some discrete numbers. So the domain is discrete. Try to be consistent with the use of square brackets. If I'm not, tell me, but I will also try to be consistent with that. So, yeah, so an image is a function. The signal is a function. So the signal is a function, is a discrete function, and an image are also functions. And if you want to say, okay, my image goes from 0 to 255, so you can say like that. So you can say image takes a real location, and then it goes from 0 to 255. Then you use the proper symbol. So when you want to describe a set, you have to use the curly brackets. So sometimes you don't want to specify view state like this because you are too lazy to write this thing, but typically it goes from 0 to 255. But it can go from 0 to 1 if you so. You can also have images that take a number and they go from 0 to 1. What about these ones? So let's say that you have an image that goes from, you have m rows and n columns. So you go from, so your discrete image go from 0, 1, 0, 1, when 0, 1 to n, and it prepares number, let's say 0, 1 to 255. But this is too cumbersome to write, and very often you say, no, I'm going from discrete numbers to real number. And depending on the context, it may be clear. But if you want to be precise, you would have to write it in this way. Okay? So an image is nothing more than a function. It is just a function. It is a function that goes from one domain to a range. And the values here are 255. Let's say that I want to say a color image. So if it is a color image, now, so let's write now a color image. So our color images will be green. So the result is a vector. So the result is a vector, and they go from 0, 1 to n, 0, 1, n, and then 3 numbers of this kind. So I put Q. The image is a function. It's nothing more than a function. And so are videos and maps and volumes and everything. So they're nothing more than functions. So now you see why mathematics is so important, because if you have a function, the right way of studying a function is using calculus and this thing, and calculus is a function. So mathematics are really important here.
I don't understand the part, right? If it's a function of two values, why only do enter with one?
This one, this is a vector.
Okay.
This is a vector. Okay, so the bar on top is a vector. And a color image, the result is a vector. That is why it also has a bar on top of the eye.
Is there any reason we use only 8-bit working color range?
No, you can use 16 bits or 32 bits, you can use whatever. Okay, good. So then here we are. So an image is a function, but at the end you can also think of it as matrix. Okay, matrix is another function. Okay, and then this is a little bit more formal. So when you have images, you talk about pixels. So I don't need to read exactly absolutely everything that is on the slide. So the important thing here is that when you talk of an image, you say each one of these squares, each one of these squares is a pixel. Okay, so the definition of a pixel is the pair, location, and the value of the image at that location. So that tuple is a pixel. And pixel actually means picture element. And R as C here, they are rows and columns. So the first index in this notation, it is the row. So you go down, and then it is the column, you go to the right. Yeah. So if it is just a single value, then it is a gray color image. If you have multiple values, you have a color image. Okay, so then this is another representation of the same idea. So you have here are the rows, here are the columns, where you specify which row and column you refer to, and then you can say the image at this row and column that I'm referring to that location, and these are scalar values, but I can put a vector that is P. He's not putting bars on top, but we do. Actually, he's using bold notation. So when you have a bold letter, bold is also a vector. Okay, so he's having the vector P that is formed by R and C, and then the image at the location P, but you can also write in this way, is the value, the pixel value. So you have two components, the pixel location and the pixel value. But the pixel is a combination of the two. Okay, so then for this particular location, you have this particular value. And this value is always, there must be some convention. The convention is to write red, green, and blue. So you have low value for the red, relatively low value for the green, a little bit high for blue. And then you have that blue pixel. So even this blue pixel, the blue pixel has a little bit of red and a little bit of green. Okay, so it's not purely blue, just 0, 0, and then something. So if you have a blue pixel, still you have some red and green line there. Okay, so how does an image form? So you have an object in the real world, and then you collect images of that object, and normally you do that with some optical device. And the optical device will have some kind of plane that projects. Okay, so you must have a light source, so something that emits energy, and then the photons emitted by the sun goes to the object. Some of the photons go away, they're collected by the lens, and they're projected into the image into the image plane. So this object is 3D, but the image is 2D. Okay. And typically, if you studied a little bit of optics, yeah. So the lenses normally they invert the images. Then this is a continuous image. So this is a continuous image, but in the computer you cannot store continuous values. So infinitely many digits for a value, for a pixel value. So you have to discretize it, and you have to discretize it in two ways. So one way is a space. So you have to discretize space, and this space discretization is the same as the one we did here. It's a space discretization that we did here, and actually the separation between two samples, that is the sampling rate, and in images it is called the pixel size. The sampling rate for 1D signals is called the pixel size for images. And something important, what is the unit of the sampling rate? Seconds. Is the unit for pixel size. So the unit must be meters. It can be 0.000 something meter, but it can be very small. Like this is a spatial. This is time. This is a space. So you are discretizing space. Okay, good. So then you discretize in space, and there is something else, that is you have to quantize. So you have also to discretize in values. So here we have discretized space, but still every pixel, every square can have absolutely any real number, but this is not, you cannot store that into the computer. You have to quantize it. So here it is exaggerated so that we can see it, but you have only a finite number of colors that you can represent in the computer. So if you use numbers from 0 to 255, you can have 16 million colors. So this 256 to the cube is 16 million. So you can have 16 million colors, you can have many colors, but you cannot have infinitely many colors. Okay, so the discrete images that we have in the computer, they have been discretized in two ways. One is a space, so the squares, they can be very small, but they are squares. And they have been also discretized in value. So they have been quantized. The discretization in value, it is called quantization. So here we have the three processes. Or the two processes. So you have the real image. This is continuous, and it is continuous in space and value. This one is sampled, so it is the space is quantile, so the space is discrete, but the color is not discrete. So you can have any value there. Here, just for you to see, you would have the opposite. So here we are quantizing the color, but we are not quantizing the space. And here you have the two. So a space quantization and a color quantization. And these are the images that you store in the computer. Okay, so yeah, this is so. Okay, good. So how do we do the sampling? So the sampling is this process of discretizing space. So discretizing space, what we will do is to one sensible way is, let's say, to compute the average color. Okay, so let's say that we are discretizing this pixel. All the colors, all the colors in that location is white. So we simply put the white color. That's it. That's very simple. But what do you do when you have borders? So for instance, this pixel here, half of it is red, the other half is white. So what should I do? One possibility is just to compute the average of those colors. So you have 3 channels, and for the 3 channels, for each one of the channels, you compute the average. So actually, it's not putting vectors here, but it is also defined for vectors. Okay, so this could be a vector, this could be a vector, and then what it says is that the continuous image, that is this one, the continuous image, you go for some range, and this range is, for instance, here we are showing this pixel here. So you go from r times delta to r plus 1 times delta. Delta is the pixel size, and so it is the sampling step. So here in rows, you are going from the location r delta to r plus 1 delta. It is the same as in 1D signals. In 1D signals, you go from n to n plus 1. What is the time if I have, say, if I have, so one to make it bigger. So let's say that this is sample n, this is sample n plus 1. So this sample, where does it go here? It goes to n times ts. This sample goes to n plus 1 ts. So ts for us is delta. Then we are going from r delta to r plus 1 delta, and from c delta to c plus 1 delta. And then you have to average. But averaging in a continuous function is computing the integral. So we compute the integral. But you have to divide. So averaging, you have to divide by the number, by the number of numbers you have used to sum. So the integral is the equivalent of the sum, and then how many numbers have we put? So the numbers we have put is proportional to the area. So you are dividing by the area, and the area is delta squared. Good. So this is nothing more than saying we are averaging the pixel, the colors that we see in this small square defined by that. And then this is in continuous coordinates. These are delta, r plus 1 delta, but I will store them in a discrete signal. And the discrete signal will say, okay, r is in the middle of the pixel. So this value that we have computed here is associated to the middle of the pixel. So you see that this r is in the middle. It is not at the borders of the pixel. It is at the middle of the pixel. Okay. So at the end, it is as if we compute the images. So it is as if we have some values. So we have, let's do it with only 4 pixels. So we have the values at these locations. So my image, my discrete image, has values only in those locations, and those locations have the average of all the continuous signal in that square. But it is in the middle. Okay, but this is something very important. And depending on the application, this can be very confusing. Sometimes in some applications, they put the pixel values, they put it in the corner. And then this half pixel creates problems. Okay, so we have quantized space. And what happens here? Okay, so this is just the sum of that. So we have pixel values, so not pixel values. We have these colors in the continuous image, and the pixel value is the average of all those. And it is the average in the three channels. Then we have the quantization of the image. So the quantization of the image, it is, you have a continuous color. So this will be the average we have just computed. But then we cannot represent everyone. So what we will do is just make a discrete approximation to those. So for instance, we can say, okay, what is the average of all those colors? The average of all those colors is all these are red, and this is the average red. And you cannot see the difference between this one and this one because we are not, our eye is not so precise. But you see this overall. You see this, the differences, right? So now you take all these colors. This is the average. All these colors. This is the average. All these colors. This is the average. So this is the table. This is a table in which you have a color. Let's say this is a function. A function in a table is also the same thing. So you have the sample value. This is the average you have computed before. And then here what we have is a quantization of that sample. And it is a stair function. So let's say that this thing is continuous. So 1, 2, 3, 4. Let me do it in some nice way. So here we will also quantize. So this will be the output. And our output will be rounding. So if you are between 0 and 0.5, I will return 0. And then I will return 1. And then, so this operation is round. It's round of items. You can also represent this. So these square brackets are the rounding operation. Okay. So we are rounding the continuous values that you have after averaging, you're rounding them to some integer. Okay, good. Then this is illustrating all these image things with MATLAB. We don't care about MATLAB, the syntax of MATLAB, but we care about some concepts. So for instance, let's say that you have a JPEG image. JPEG, you are already familiar with this name. So JPEG is a file format to store images. So you have a JPEG image, you read it, and then you ask MATLAB what kind of object you have. And you see it is an unsigned integer of 8 bits, which is what you would expect. So unsigned integer of 8 bits are the numbers going from 0 to 255. Okay, that's fine. And then what is the size of that? The size of that is 600, 1203. And then we recognize, okay, this must be the width, the height, the width, and the number of channels. And we have 3 channels, red, green, and blue. Okay, that's good. Then represent that image. And we have that image. Okay, and here you have to recognize something. One thing is the image information. The other thing is how you display an image. So this image is distorted, right? Faces are not like that. Why is that? Because this image is twice as wide as height. So, and this, the relationship between this length and this length is not twice. Okay, so you have compressed in one direction. So one thing is the true numbers and the true information. Something else is how you display that. So the display is not always just a perfect, faithful representation of the underlying information. Okay, so that is some command in MATLAB to make it more faithful. So true size, then you have the right representation. But this concept is already important. So something is the signal itself, something else is how you draw that signal. Okay, then, okay. So we have an image. Here you see the origin. Let's go one back. So the origin is here. You see the 0, 0 coordinate is here, or the 1, 1 in MATLAB. So 1, 1 is here. And 0, 0. We will try, so the more mathematical way is 0, 0. The origin in MATLAB, that is a programming language, the origin is 1, 1. Okay. But, okay, the origin is here. And our signal is defined, we follow our notation before. So if we follow our notation before, it goes from 0 to 600, 0 to 1200. Okay, good. What if I take a crop of that image? If I take a crop of that image, now this is not the 0, 0 point. So this is starting somewhere like 600 something, and then it doesn't go to 1200. So the coordinates, so these ones, they go for different ranges. Okay, but it is also an image. An image, we say an image is just a function. A function doesn't need to start from 0. It takes some argument, so some row argument, some column argument, and the rows and columns, they may start at 0, that is the normal thing, but they may go for something else. So here they are going for something else. And the top left corner, now it is not the origin in the sense of 0, 0. Okay, so it is the first pixel, but it is not the 0, 0 pixel. Okay, good. Then you may reassign the rows and columns if you want. So now you say, okay, I forget that it is coming from a bigger image, and now my top left corner will be again 0, 0. So you can do whatever. So as long as you are consistent with what you are doing, you can do whatever. Okay. So then, okay, so now I repeat the same process, but now with a different kind of file format, that is the GIF format. So the GIF format will read the image, and I will not comment for the moment this amount what it is. So we read the image, and if I ask what kind of data you have, unsigned integers of 8 bits, that's fine. But then it is surprising, we only have 2 channels or 2 sizes. So we don't have 3 like before. So before we had three channels, now it seems that we have a single one. And when you make the representation, it is rather weird. So this is another nice image. So what happened? And what happened is that we didn't use the color map. So now when you say, okay, represent that image, but using this color map, and then you get the right image. Okay, so then the question is, what is a color map? So the color map is a table. Okay, so our image is, I will explain it here. I think it's more clear. So let's say that we have a 2-color image. So this is a 2-color image. So true color, for each pixel, we have some values. So let's say that for this one, we have the vector 220, 107, 41. And then for this one, I also happen to have the same color. It's the same color. So how many numbers do I need to represent that? So I have 16 pixels. For each one of these 16 pixels, I need 3 numbers. So this true color image needs 4 times 4, that is the 16 pixels, times 3 numbers. This is what I need. Okay, then let's say that I only I go over all pixels and I discover I have only 4 values. I have only 4 values. How many numbers do I need? So I can say, I can construct the table, and say, okay, in this table, I will have, this is my index, and this is my color. One of the colors will be 120, 107, 41. And then I say, this is color 0, this is color 0, and the same for all the other colors. How many numbers do I need now? I will need 4 times 4 times 1. So it is 3 times smaller than this. But wait, because we have to keep these numbers. So these numbers are 3 times 4, this is 12. Okay, but still, this is much smaller. This is 48. This is 16 plus 12, only 28. So this is about the half the size this one. A little bit more than a half the size. So these ways of representing images, they're called color maps. Color maps. So when you read an image, the images, the values here, they are the indexes of the color that is in your table, in your color map table. So the color map is the table. And then that is why, yeah, you don't have a third channel. So you only have the indexes. And then when you use the color map is when you get the right representation. Okay. Yeah, all this is the same. Sometimes color maps are normalized, so you divide the color map by the table by 255. So instead of storing these numbers, you store these numbers divided by 5. So it is a number between 0 and 1. Okay, this is what this one is representing. Fine. Good. So then this is this column map table, and then this index points to a column map. And if you want to recover the original size, because this table has been normalized between 0 and 1, you have to multiply back by 255, so that we recover the intensities in the original channels. So here you have two images with it is the same image in principle, but this one is true color. So you have 24 bits, so 3 bytes, 1 byte per channel, and you have here the color map image in such a way that we only have 256 different colors. So this same kind of color table. So you only have 256 colors. So you are limited in the number of colors you are allowed. And each one of the colors here has 24 bits. This is the meaning of this. Okay, so we have the color map has this size, but then the colors inside the color map, they have 24 bits. So here you are able to represent 16 million colors. Here you are only able to represent 256 colors, only 256. And still, most of the image looks okay. If you pay very much attention, for instance, this bright spot here, the bright spot looks different because you are limited by the number of colors you are allowed to use. Okay, so they were not exactly in my example. In my example here, they were exactly the same color, but maybe they are not. Maybe, for instance, this one was similar, but not exactly the same as the other one. But then I am approximating this color by this one. Okay, there is an approximation process there. And then if you pay attention, you see the approximation. But very often, if you look from distance, and for instance, for videos, the images are changing very quickly, you will not be able to notice these differences. And what is the size of this image with respect to this one? How much larger is this one with respect to that? 3 times. 3 times larger, because for every pixel here, I need 3 numbers, 3 bytes, but for each pixel here, I just only need 1 byte. So this will be 3 times larger than that one. I have made a compression by a factor of 2/3, and almost 3. But again, if you pay attention to the specific details, you see differences and you see the approximation. So there is a small variation here, even if it is quantized. So even if you compare this to the original image in the real world, you could also see that there are some colors are approximated. But here you see the jumps between the approximations. This is nothing new. This is nothing new. Yeah, this is all. This is color MATLAB sim. So we don't care about that. Okay, let's make a break. 10 minutes. So it's 22. So during the break, I have made an interesting question. How do you approximate these 60 million image, 60 million color images? So the colors, how do you approximate them? You can think of the image that we have in here. So you can think of these points as a vector cloud. So for every point you have a vector of 3 components. So we have a cloud of points like this one in 3 dimensions. And then there is a vector quantization process that groups the vectors in regions. And here they are very well separated, but there might be some continuums here. So they may change smoothly. But then all these vectors you approximate by this one, and this is the one that you put in the color map. Okay, so then, yeah. Okay, so then I can construct column maps of any kind. So for instance, I can construct a vector that goes from 0 to 1. That will be one of the columns of the column map. And I can construct several column maps with that. I can put 3 times the same. So you see that it would be 0, 0, 0, 0.039, 0.039, 0.39. So the numbers will be repeated 3 times. Or I can have this rank and then 0, 0, or 0, the rank, and 0, or 0, 0, and the rank. Okay? So each one of them will be a different kind of color maps. So this color map, in which the 3 numbers are the same, will be a gray color map. So actually gray images have this property. So the red, green, and blue channel, they have exactly the same value. And this color map, all of them will be red because the green and blue channels, they are zero. And this color map will be completely green because the red and blue channels both are set to zero, the same for this one, that is blue. So then I can, for instance, I can take, remember that we have this color image, and this color image, they are both here. So for every pixel, so let's do it. So for every pixel, I have a pixel here. And let's do it with 3 sequence. So for every pixel, I have a red, a green, and blue channels. But this is the same as if I have, this is the same as if I have 3 images. One is red, one is red, the other one is green, and the other one is blue. And each one of these, the same for the other two, each one of them, they only have a value. Here you would have the red, here you would have the green, and here you would have the blue. So either I have an image goes, and lazy here, I don't want to say 3 times 3. So that goes into a vector, or I have 3 images, the red one goes from a location to just one column, and the same for the other two. So I would have the green one that would be exactly the same, and I have the blue one. So either have a vector valued, this would be a vector. So either have a vector valued image, or I have 3 images that are scalar valued. So this is vector valued. Value is a vector, this one, or I have a scalar image. With a value inputs. The result is a scalar. Okay, so now I can take the 3 images as a scalar images, and I can represent them with a polar map because it has a single value. I can represent it with a gray polar map. And then let's see if they make sense. So for instance, the grapes are blue. So if the grapes are blue, I would expect much of the image or much of the intensity to be coming from the blue channel. So you see, this has a large value. It is darker here, it is darker there. And these regions that are red, so these regions that are red, they are brighter here than there and there. So you see the outer part is dark because it is red. So the intensity should be coming from the red channel, not from the green or the blue channels. And these are lines here that are green. Here I barely see them, but in the green channel I see them very well. Okay. And I can represent them like that. I can, this is red, green, and blue channels. Or I can represent them like this. So I can use the red color map to represent the red channel, the green color map to represent the green channel. So again, there is a dissociation between what the information is. So the information is just a scalar. So this is just a scalar. It is just a number. But this number, you can represent this way, which makes sense. But you can also represent this way, which also makes sense. So you have to dissociate representation of a signal and what the signal is. Okay. A lot of representation. This guy likes repeating a lot the same idea. Yeah, and then you can write the images in different formats or whatever. So we don't care. Okay, then images are matrices. So if an image is a matrix, then I can add two matrices. So I can have this image plus this one, and then I will have a mixture of the two. So it is simply just the addition of the vectors at the appropriate notation. And then when you do that, there are some things to take care. So first thing is this image is bigger than that. So you cannot add two matrices of different size. So you have to make them different of the same size. So you have to crop a region here that has the same size as this matrix. And this is what is done here. So this syntax here, it is somehow taking, this is one of the images, this is the other one. So this part is taking all the channels from this image in this region. So this region is making the crop. And then they are vectors, but they are unsigned integer 8 bits. So they go from 0 to 255. So what happens if I have this? My numbers are, I don't know, I have two images here. I have two images. More and less, see. So here I have 200, which is a correct value. This I have 100, and then I store that in that format, in that number format. I cannot. This is called overflow. I have gone over the maximum value that I can represent with this. This I can only represent from 0, 1, 255. I cannot represent 300. So what do I do? First, you convert that to a double. So now you have floating points. You convert this one to floating points, and then you can add the two. You can represent 300. Then you divide by 2. You can go by to 150, and then you convert it back to bytes. Okay. So when you do these kind of operations, you have to be careful with what you are doing, because you might have to be going into overflow. Okay, so then we could have this result. And you do the same for the three channels. So you add the red with red, green with green. Okay, yeah, I mean, it's explaining all that. Okay, what if I multiply? If I multiply, I have almost the same problem, even bigger problem. What is the maximum? Let's say that you have two images that are 0.8. What is the maximum value we can have? So I multiply the two. Now it is not an addition, it is a multiplication. What is the maximum value I can have? So it is 255 times 255. How many bits do I need to store that number? It's not difficult. You need 16 bits, right? So you would need to store this number, put it at the same time. So to store this number, you need 16 bits. So let's do that operation again. So what we will do is this part is taking care of the cropping. Then we convert to double, we multiply, and now I can do something. Okay, so I need this. I have done the operation in floating points, so I don't have any problem. And I have to store it in 8 bits. So I can do the following. So why don't I do this thing? Okay, so let's say that this is the multiplication image, so the multiplied image, and it goes, I don't know where, but it goes, let's say, to 60,000, and the start, the smallest number is 200, let's say, okay? So, but I have to store it in 8 bits, so I will quantize it somehow. This has to be with 8 bits. So how do I map it? So one possibility is doing this. Okay, so I have 0, 5. I use this line. I use that line. What is the equation of that line? Okay, the equation of that line is very simple. So quantized will be. So this has to go to 0. So it needs to have a positive slope. Okay, so a positive slope. So that means that the sign of the multiplication has to be positive. Okay, then I have to map it. What if I do this? I will give you the answer and so what I'm claiming is that this is the slope of this. So that is that slope. And then this m, that is the minimum value. So let's say that the image takes the minimum value. So if it takes the minimum value, will be 200 minus 200, that is 0. 0 multiplied by anything is 0. It goes to 0. What if it takes the maximum value? If it takes the maximum value, so it will be maximum minus minimum divided by maximum minus minimum, that is 1, and then multiplied by 255, that goes to 255. And it is a line. It is a line because it only participates to degree 1. So that is a line. That is the equation of a line. Okay? It has this shape. Has the shape A, R, N, C. So that is a line. And now the result, this quantized, is between 0 and 255. It is true that it is a floating point, but then you can turn it, so you can round it, to 8 bits. So you see that is the multiplied image minus the minimum divided by maximum minus minimum. You have to do the same for the 3 channels. So this transformation is very important. This transformation is very, very, very important. So this you need to know by heart. Okay. Good. Yeah, then it is explaining that. This saying, yeah, you can do that for any image. It doesn't need to be after multiplying. So you can take any image and you can see what is the minimum, what is the maximum, and you can enlarge it so that you're increasing the contrast actually. So we will study more about the contrast, but you see that this image is brighter, so it has more contrast than this one. So the dark is darker and the bright is brighter. That is contrast. Okay, good. Then I can compute all kind of differences. So for instance, this scaling is called linear scaling. This linear scaling, this operation is called linear scaling because it is a line and and you are scaling the gray values. So, for instance, let's say that we have two images. One is one image that has full resolution. We have all the details there, but then we save it with quality 0 JPEG. Okay, so quality 0 JPEG. It has a it is a smaller, so it is a kind of tree like the column map. It is not exactly the same, but you are reducing the amount of information somehow, as we did with the column maps, and then we scale them. So we compute what is the difference between the two. We compute the absolute value, so we don't care if the difference is positive or negative, and we do simply a linear scaling, and this is what we see. So we barely see anything, and the reason is that there must be some very bright spot, and then all the rest remains very low. So yeah, we haven't seen histograms, but yeah. So what we can do is something. Okay, so this is a linear scaling on the difference image. What if I take the logarithm of the difference image and then I scale it in a linear way? Or I take b squared and I put it as a byte. So you see that different transformations, depending on what you want to do, this linear scaling may be fine. Not in this case, but in this case was fine. In this case also, in which we multiply the two, it was fine. But not always. Sometimes you have to represent the image in some other way. And again, you have to distinguish the signal from the representation of that signal. So the signal is this one. This is the signal. But then we are representing it this way, this way, this way. And in each one of the representations, we are highlighting different features of the signal. But the signal is the same. The signal doesn't change. Okay, and then, yeah, this is very specific to MATLAB. So, yeah, we don't care about this. Skip all that. Any question up to here?
Like the food that you have done, or what was the explanation?
This one? No.
Yes.
Yeah. The exponential.
Like,
This one.
no, the explanation, like, what is that?
This is, you multiply the two images. So the multiplication will have a range. I have it basically that it goes from 200 to 60,000. But then you have to, you cannot keep this multiplication into 8 bits. So you have to convert it to 8 bits. So how can I do that? So I can look at what is the maximum and minimum value of this range. And then I apply a linear transformation that takes it from 200 to 60,000 to 0 to 55. Still, you are discrete, continuous. So you might have a value here that is, I don't know, 30,000. And after the multiplication, it goes to, I don't know, 23.75. So you are floating point. But now, if you round, you are in integers. What else? No other questions?
But like,
Yeah.
you said multiply two images.
Wait. Yeah.
You have, like, when you have two images, is that something, something?
When you have two images, you have the same problem, but we solve it in a different way.
Okay. So, okay, so
Sorry, it's always confused between the.
when you add, you sum, no, both.
Yeah, when you add two images, we here. So we add it, but then we divide it by 2.
Okay.
Actually, that is interesting. Let's say that this image has 8 bits. This image has 8 bits. The addition, how many bits you need to store that. 9 bits, exactly. Okay. 9 bits, and then you are dividing by 2. How many bits do you need for that? 8, because I'm dividing by 2. Dividing by 2, the bits is 2 to the 9. If I divide by 2, it is 8 bits again.
And when do you need to multiply like animate?
It depends on every problem. Like, for instance, very typically, when you want to put a mask on an image and show you what a mask is. So, say image masking. Masking, say binary masking. So this is, yeah, something like this. So you have an image, you compute a binary mask, and then sometimes you want to multiply the original image by this mask. So you have to multiply. This mask is between 0 and 1, or 0 and 255. Right. Yeah. Questions?